Alright, so the two examples on page 10 are not numbered. Don't know why, don't remember why, but regardless of that, let's go over them. 71, we're converting 71 and 895 thousandths of a degree to degree minutes seconds. Okay, so remember, a degree can be divided into 60 equal parts called minutes, and each minute can be divided into 60 equal parts called seconds. So those are smaller increments or smaller parts of a degree. So 71 is a whole number, right? So we'll put this down here, and this is 71 degrees. We want to see how many minutes are in 0.895 degrees. So we take 0.895 degrees and convert that to minutes. So remember, 1 degree is 60 minutes. So notice how the degree and the degree can be canceled and we're left with minutes. So you multiply that, take your calculator, multiply that, and you get 53.7, and we're in minutes. Now 53 are 53 whole minutes, so we're going to put this next to the 71 degrees. Oops, sorry. I just said degrees, so that's why I wrote that down. So minutes, and we have 0.7 of a minute. So you take 0.7 of a minute and convert it to seconds. So 1 minute is 60 seconds. So just like on the previous part, that unit and that unit cancels out. You're left with seconds. You multiply the two together and you get 42 seconds. So 42 seconds. And that would be the angle in degree minute seconds, the same sized angle. Okay, just in a different form, in degree minute second form. Now, if you had ended up with a decimal number here, the directions would either tell you to round it to the nearest second, or just leave it as is with a second, symbol after it. Okay. Now, for the other example, you start off with 40 degrees, 27 minutes, 56 seconds, and now you want to convert it from that to decimal degrees. Now, think of this as 40 degrees plus 27 minutes plus 56 seconds. Okay, so we want to see 27 minutes is what part of a degree, and 56 seconds is what part of a degree, and then we're going to add them together. So 27 minutes, we're going to convert it to degrees, and remember, 1 degree is 60 minutes. Minute and minute cancel out. You're left with degree. 27 divided by 60. Again, take your calculator and you get 0.45 degrees. Okay? Now you take the 56 seconds. 56 seconds, we want to convert it to degrees. 1 degree is 3,600 seconds. So again, second and second cancel out. You're left with degree. And this is this non-terminating decimal. So 5555 forever. So remember, we're going to add these together, and we get 0.465, like that, degrees. And so we had the original number is this one, right? We have the 40, that's a whole number, 40 degrees, and then this, we took the 27 minutes and the 56 seconds, added them together, and this is what part of, that's the decimal part of the degree. So we combine those, and our final answer would be 40 and 46. Now, since we're rounding to 3 numbers after the decimal, this means this continues, right, forever. So when we round right here, this ends up being a 6. And that would be the answer in decimal degrees. So for this problem, we went from DMS to DD. Alright, so for example 5, they want you guys to find the arc length of a circle with radius 27 inches. The angle is 160 degrees, and they want you to find the arc length. They want you to find this measure right here. Okay, we know that this is 27 inches, and we know that this is 160 degrees. So to make it a little bit more realistic, I guess, 160 degrees is approximately right here. If we count this as 160. So we're looking for this arc length right here when this is 27 inches and this is 160 degrees wide. Okay, so we're looking for that arc length. So notice the formula is S equals R theta. Theta has to be in radians. So 160 degrees has to be converted to radians. Remember we did that at the beginning. So pi over 180 is the conversion factor. I can reduce that. And I can reduce by 2. So 8 pi over 9. That's the measure of the angle. So now we're going to take the radius times 8 pi over 9 radians. Now 9 goes into 27 3 times, so this becomes 24 pi inches. Now this would be the exact answer, but normally we don't talk about length in terms of pi, right? We convert it to a decimal. So when you do that, and we can round, we get approximately 75.398, it goes on forever. So we're going to round it to the nearest tenth, so 0.4 inches. So this is the approximate answer, this is the exact, this is the approximate. Alright, so for example 6, we're now talking about circular motion, linear and angular speed. Linear speed is what part of the arc, the length of the arc divided by time. And so for example 6, and we're going to talk more about example 6 and 7 in class, but let me just go over the ones in your notes right now. Example 6 has a second hand that is 8 centimeters long, okay, and it's asking, you know, what is its linear speed around the face of the clock. So we need to know the circumference of the clock, or not of the clock, but necessarily, but of the distance that the 8 centimeter second hand covers. So here's the clock. Here's the 8 centimeter second hand right here, and it goes around, right? It goes around the clock, and it takes 60 seconds to do that, right? That 8 centimeter second hand takes 60 seconds to go around the clock. Now how much distance does it travel? What's this distance right here? What's the circumference when the radius is 8? Well, remember the circumference of a circle is 2 pi r. So the circumference that it covers is 2 pi times 8, which is 16 pi centimeters. So we're going to put 16 pi centimeters right here, and it takes 60 seconds to cover that much. So when you reduce that fraction, you get the linear speed, or the velocity, is 4 pi over 15 centimeters per second. And again, changing it to a decimal, it's approximately equal to 0.83, rounding it to 3 numbers after the decimal, centimeters per second. So the one on the top is the exact linear speed, the one on the bottom is the approximate. Alright, so for example 7, they want to know the angular speed of a circular blade as it rotates at 2400 revolutions per minute. So angular speed is how quickly the angle is changing over time. Okay, how fast is it moving over, is it changing over time? So theta is the angle and t is the time. That W, like curvy W that you see right here, that's a Greek letter omega, and we use that to represent angular speed. Okay, that's not in your notes, but I'll talk about it in class, but you can write it in your notes right now if you'd like. So we have 24, let me just go ahead and change that, 2400 revolutions per minute. Now, in order to be angular speed, it has to be angles per minute, but this is revolutions per minute. But remember, we know that 1 revolution is 2 pi radians. Okay, so now we can have revolution and revolution cancel out, and we're left with radians over minutes. So that's going to be 4,800 pi radians per minute. And this is now the angular speed. Before I go over example B, 7b, let me help you make a connection between linear speed and angular speed. So this here that I have, this is linear speed, v equals s over t. But remember how s, from the arc length formula, s equals r theta. And so if I break it up like this, r times theta over t like that, it's still the same thing, right? I just set it up a little different, but it has the same value. I see theta over t, and that makes it r times omega. So what ends up happening is that v equals r omega. This part is not in your notes. Again, I'll go over it in class, but there is a connection. Here's the work. Here's a connection between linear speed and angular speed. With that said, we can now go and do letter B. Okay, so for B, it's asking for the linear speed of the tip when the blade is the radius of the blade is 4 inches long, right? So they want the linear speed, but we know that v equals r omega. V is a linear speed. This is what we're looking for. We know that the radius is 4 inches, and we know from part A that the angular speed is 4,800 pi radians per minute. So we multiply these together, and we get the linear speed is 19,200 pi inches per minute. Notice how radians no longer plays a part in the final answer, because radians is radians is a unitless measure. The only time you'll see it is when they ask for angular speed, like they did in part A. But in part B, it's gone. It's a unitless number. So the linear speed is 19,200 pi inches per minute.